Yeah, so I guess one thing I should imagine is a positive semi-proximal, then the or positive proximal the I guess then the so in this case minus lambda I or the some complex eigenvalue cannot be an eigenvalue if this happens, and the same for this case also because you can apply the orbit theorem. So you can generic point and you take the orbit and you get the non-proper convexity. So only positive ones are eigenvalues of the same norm in the largest case. And also in the smallest case here. Okay. Okay. So that's not said, but that's true. Okay. Okay. So that's one thing you need actually. Uh, Right, so we should start with the higher convergence group, right? Today. So if you have an unbounded sequence of projective automorphism, and you can consider these as in SL and plus one R, and you can always. So this is just the subspace of the MNRR normalized by this space because. Up to positive scalar because there's a one-to-one correspondence here. So okay, so that's sorry, this is not open subset, it's a closed subset, right? Okay, so sorry about the mistakes here. So there's so many there. Right, and then the this will converge to some element. So given a sequence, we can always find the subsequence convergence. Because this is actually a projective space, right, up to double cover. So this is compact space, so you can always find the convergence subsequence in this. Okay, and this is some endomorphism, so it's not may not be invertible, right? So it's no longer in SL plus one, so it could be in some other subspace. And of course, since this is an endomorphism, there is some corner and the range. And of course, this is a usual theorem here of the corner range theorem. Okay. Uh, so usually this will be n plus one, but we drop by one dimensions here. So that's why this happens. And for any compact set, this will it will always converge to some subset because in the image of G infinity. So this is just the image of K under the G I am G. I mean the G infinity here. So this is a limit endomorphism, and also so given a convergence sequence, you can also multiply by G, and then so this is if you just multiply by G, you see this is pretty easy to see, and the corner and also image like that, and if you multiply on the left, then it also converges to this. And of course, the corner, you need to put the G inverse here to get to the corner here, and then image is the same. So because this is just the theory of matrix, you just need to write the theory of matrix. So G infinity can be obtained by taking limits here also by mg is the maximal norm of the elements of G in the matrix form. So these are all in SLNR, so you can do that. Of course, you can do it for GLMR also, right? So this is so given unbounded sequence, if this is convergent, then it's called the convergence sequence, and this is called the convergence limit, and this is called the convergence limit in S. Okay. So these are useful theories, and so you can also do this for PGLR, and Of course, this was originally developed for SO21 by Tukia, but of course, these are just a subset of these kind of theories. And then we have a KAK decomposition or polar decomposition, Cartan decomposition. So if you don't know Cartan decomposition, you should look at the book by the Helgeson. So any element can be written like this, and the Di is positive diagonal like this. The S1M is subspace defined, denoted by this. So you can denote the subspace span by these. Then the so we can assume Ki converges to K infinity and Ki hat converges to K infinity hat. And this is conversion in RPN, so you can assume that. Then you can write like this for PGL and R case, PGL in R case. And so for convergence sequence, we can also define the A hat and N hat like this. So this is the kernel and image. And then you take the intersection and you get these. And so if you have any orthogonal element, you can estimate like this. And so the norm of G can actually be estimated by these square like this, because G can be written as K dk inverse like this. So that's why this happens. And the way to understand this convergence limit is that there is some number between 0 and plus 1, where the ratio always goes to 0 or bigger than MA, and then it's bigger than epsilon for J less than MA for some uniform epsilon. Okay, so for any sequence you can do that. So this is strictly decreasing. So below MA everything goes to 0, but below MA its ratio is bounded. And then also there's MR, where this is J M for M plus 1 is bounded for the ratio, and then for up above that, that's always goes to infinity. So this is the smallest eigenvalue, so everything is bigger, but there might be somewhere it's bounded. Okay, and so this is in S right. Of course, this is always in SLM plus 1, so this will always go to 0 anyway. So to understand n hat, you just have to understand the geometric limit of this, and this is a geometric limit of that, and so on. Okay, so these are all the things you can do. So I don't think I want to prove this. It's not really difficult. It's just the estimation with these inequalities that I get, and also next we also define these kind of subspaces. And I want to skip that. But anyway, so uh, and also I can prove that these are sets are described from omega, but their intersection with the closure is always in with the boundary. Okay, and so on, and okay, so that's all. Yeah, so please read through it. I cannot really explain too much due to time, and so I will go to the convexity of projective field 4.1. So you define the convexity orbifold to be convex if it's diffeomorphic. So there's spelling error, and the projective quotient of convex domain in open hemisphere, and the yeah, and then real projective envelope is convex if and only if developing mass sends the universal cover to convex domain. Okay, so if you define it like this, then you can always show that developing map also does that, and it's properly convex if and only if the developing mass sends universal cover to properly convex sub an open patch. Okay. and it's not properly convex and not complete affine. So complete affine case is when the development is a portion of a complete affine patch, so in that case it has an affine structure. But suppose it's not, then the holonomial is actually reducible and is now fully affine space of dimension I with the common boundary. Okay, so some fixed subspace in here, and then this holds for any convex domain and projective group acting on it. Okay, so the basic proof is that if it's properly not properly convex, then you can show that this closure is always some gray sphere joined with K, and so then this is reducible, and then you have to look at the interior and so on. Okay, so that's for this. Okay, and there are some convexity results that I am talking about. So, for example, if you have a convex domain and the boundary has always a convex neighborhood, then it is convex domain. So this can be proven by some sort of broken projective geodesic argument. Okay, so that's and there are some needed facts later, but I don't want to spend time on it. And, next important thing is that if Gx on convex domain is so that it's a compact orbifold and it has only unit no eigenvalue element, then this is also complete affine. So that's an important theory, and the reason is if you have a G is only a unit eigenvalue, then it's also potent and has a unit potent group finite index. Okay, so this was I showed that last time, and so this means a unipotent group has a fixed point in the dual sphere. So use stardust 2. So there's some hyperplane where axon and this is the intersection has to be empty. Okay, with the, it's not empty, but closure is not empty. So actually omega is in affine space. So the group of affine, so Gx on A is a group of affine transformation because it fixes P. Okay, so that means it acts as a affine transformation here. The discrete affine also potent group is disturbed by the theorem of this one, and then by lemma 2, it's so some free show that this case is complete. Okay, so I should write here affine maybe later, I guess. Yes. Right. So there are lots of little mistakes, so you should please look at that. And yeah, I want to skip that. And the important thing is the Benoit theory here. So Benoit studied lots of these. So you have a discrete group here, and it acts on properly on convex domain, so that this is a compact orbifold. So actually, if it's discrete, then this is automatically true. I said that in the before, right? And then but if it's not discrete, then they will be called sweeping action. So it will be done later. So if you has any, so the following are equivalent. So every subgroup finite index has a finite center. Every subgroup of finite index has trivial center. Every subgroup of finite index irreducible. That is. So if you every finite subgroup of finite index is irreducible, then it's called strongly irreducible. So that's the definition of strongly irreducible. And the Zariski closure is semi-simple. I should say simple actually. So Bernard wrote simple, right? So, but I think I wrote semi-simple, but it should be simple actually. But semi-simple is also correct. But anyway, so gamma does not contain infinite nilpotent normal subgroup. Okay, gamma does not contain infinite abelian normal subgroup. Okay, so those are all recurrent, and it's proven in the other paper. And the center of group is called denoted GG, and the virtual center is a subgroup of C. So that each element is centralized finite index subgroup of G. And right? So G acts on X co-compactly if there is a compact set, so that this is true. Okay. So that's the definition of action of being co-compact. Okay. So it might be stronger than just the quotient being compact. Okay. So theorem 1 point. Maybe I should move that to earlier point. Okay. Right. Yeah. So I guess you should point that out if you see that. Okay. So 4.9, suppose that virtually center-free discrete group acts properly on domain so the omega gamma is compact, then every representation of the component containing inclusion also acts on compactly. So this is an important theorem. So if you have some point in the component that acts as a divide this domain, so this means dividing, okay? Then everything else in the component will do the same. So this is a sort of closeness result. Okay. Okay, so this is so that's proven also by Goldman and myself, but N is 2 and N is 3. And then uh, so uh, uh right, so Goldman Ingan Kim did it for S N is 4, sorry, this is so so we need to do the general case. Uh, I will correct that. So then the uh, discrete, yeah, this is should be n is 4. Okay. Discrete group of SLN plus 1. So if you just have an action into properly convex domain, then actually, so opposite to this case, when there is some center, you can write it as a strict join of this properly convex open domain. Okay, and um, I should say this is interior of that really. So maybe this bit wrong. And omega is the image of this open direct sum of domain. Maybe I should say the interior of that, right? So and gamma I prime is acting on each kj. And then gamma I is arbitrary extension. Requiring to act trivially on so have eigenvalue 1 associated with this direction. So you can restrict this uh, gamma prime to ki, and so let's denote gamma I by extending this by the some requiring to be trivial action on this kj. And so then there is some center, this R L minus 1, which is diagonalizable and acting trivially on each kj. Okay, so then the fundamental group is actually a subgroup of this trivial extension. Okay, so that's the result, and it acts on compactly and discretely in a semi-simple manner, and of course, Cholesky closure is this G1 to GR, and the GI is some semi-simple group acting on this E group, and G J act trivially on KJ for J trivial. So the virtual center is actually in this group RL minus 1, corresponding to some subgroup of this. Okay, so that's an important theorem, and of course, there's some example where the group acts properly on product of two hyperbolic space, but restricts to non-discrete group for each vector space. So this group, which I denote by gamma prime, this could be not discrete, even though this is discrete. Okay, so there are such examples, and So every normal subgroup finite index is virtually central. Okay, so that's another theorem. Okay, so that's so there are many results by Wei, and then the Wei proved that the properly convex domain with the sweeping action. So sweeping action means that this is omega mod gamma is a co-compact action. Okay, so co-compact action, but the quotient is not required to be Hausdorff. Okay. So of course, if you require it to be Hausdorff, then the G is forced to be discrete, and then it's just the orbifold case. Uh, so then omega equal to convex hull of orbit, and so on. So there's some generalization of a Benoit's result for the sweeping action. So that case we have any. So if there is any subspace where Gx1, then the L is closure is empty, but the G omega is empty. Okay. Right. This has to be proper subspace, proper dimension, lower dimensional case. The this Gx1 compact properly convex set, then the K must meet the this domain. Uh, and if it's G semi-simple, then all the items up to last conclusion proposition will hold. And this will be just closure will be just join, and G is if G is semi-simple, then the closure of G has a virtual center containing some group of diagonal projective automorphism. So they are GL and acting trivially on group. So actually, these are diagonalizable group, not just that. Okay, so right. So this is a generalization of a previous theorem for the sweeping action. And I will skip the proof here. And right. So these are again some technical theorem I need later. Okay, so I think yeah, again that's the same. Okay. So let me go to the so I will rest 5 minutes and then start with the Bloomberg